Okay, few announcements. The lab is due this week. I presume most of you have started by now. Okay, so please make sure you make steady progress. Don't keep it off or put it off till the very end. You will only find yourself in a time crunch. Okay. I did say that once the lab comes in, we will have to have a midterm because 1 month has gone by. So I scheduled it for Tuesday over Monday because I wanted to give a little more time after the lab is due for you to catch up on the material that we have covered so far. So it's an evening exam in this room, 7 p.m. Okay. Some of you, or not some, but whoever is registered with disability services needs any accommodations to be made, please email me so that we can deal with those cases appropriately. Okay, don't wait until the last minute for that. Okay. If you have any conflict whatsoever, which typically means another midterm scheduled at the same time on the same day, also let me know immediately. Okay. So I will send out an email about this as well so that everybody has this information. With regards to labs, you can always, if you have questions, that is, you can send me email, talk to the TA. There is also a bulletin board on Piazza, which very few people have signed up. There's a note on through Moodle to go there. You can of course ask questions there if you want anonymously, and they'll be answered, and you can see other people asking questions and so on. Okay, so do keep a eye out on similar questions being asked in those forums, right? Because I think most of you haven't even bothered to sign up, even though I had announced very early on. It's a resource that you can use as appropriate. Any questions about the lab or the midterm? High level questions, that is. Okay, I will make a sample exam available at some point on Moodle so you can get a feel for what a typical exam looks like. Okay. All right. So let us continue the discussion on synchronization. So quick recap. Last time we were basically talking about synchronization from the perspective of locks. Okay, so I said locks are simple synchronization primitive that have two methods, acquire and release, that you wrap acquire before a critical section and a release at the end. So any critical section has to be wrapped around by a lock. Okay, basically we looked at how locks are implemented by the OS or by a library using hardware primitives. Okay, the two that we studied were enabling, disabling interrupts and the test and set instruction. Okay. So we'll continue that discussion from that point on and look at the second primitive. Actually, not just that, we'll also look at monitors today. We'll start with semaphores. Okay. I think you must have encountered semaphores in some shape or form in 230. I will nevertheless reintroduce this construct. We'll see what it does for us, how it generalizes the notion of a lock. Okay, you can do some more interesting things with semaphores that we'll see what they are and how you can use them, and we'll also look at how to implement it. Okay, because this is an OS course, we will always be interested in what does the OS have to do in order to provide this feature. In this case, it's going to be semaphores. Okay, so they were invented in the 60s by computer science researcher by the name of Dijkstra, who's no more, but he had several important contributions that he made. One of them was semaphores. In a couple of classes, we will study the dining philosopher's problem, which is also something that he came up with. Okay, so you probably encountered semaphores before. Okay? So there are multiple ways to think about what a semaphore is, but give me a sense of what you did in 230 for semaphores. Okay? Somebody said last time that you heard of semaphores in 230. What aspect of semaphores did you learn about there? Any? Yes.
I can only recall using them as binary semaphores.
Okay, you can recall using them as binary semaphores. So semaphores you can just use as a pure lock abstraction. Okay, we will see that they can do more than that as well. Okay, so first let me define what it is. Okay? Semaphores, at its very heart, is simply an integer variable. Okay, it's nothing more than a simple integer variable. Okay, except that you can update this variable using special operations. You don't muck around with it like you cannot do I equal to I plus 7 or some such thing that you could do with a normal integer variable. This integer variable you modify, which means you increment or decrement using two special methods that we will encounter shortly. Okay? And those are your atomic methods, atomic instructions. So it's an integer variables that can only be updated using two special atomic instructions. They are wait and signal. We'll talk about them in just a moment. Okay. Now what can you do with semaphores? Okay. So you can use them in variety of different ways. Okay. The simplest way is what are referred to as binary semaphores, which are essentially the same as a lock. Okay. The reason they are referred to as binary semaphore is that integer variable, when you use it as a binary semaphore, can only take two values, 0 or 1. It's binary. Okay, that's why they are called binary semaphore. Okay. The most common use of the binary semaphore is as a lock, where the value is 0, is equivalent to the lock being in use, and if the value of the semaphore is 1, it is equivalent to the lock actually being free. Okay, so the value indicates the state of essentially a lock, which is what you use binary semaphores for. Okay. So the value can vary between 0 and 1. It's initialized to free, which is value equals to 1. Okay. If you use it in this fashion, it is referred to as binary semaphore, also referred to as a mutex, okay, for mutual exclusion. Okay. That's just one way. Another use for it is you can use it in a generalized form called a counting semaphore. The counting semaphore, you can use this as a lock for multiple resources simultaneously. Okay, rather than having one resource, let's say you have n resources of the same kind, you can use this as a more generalized lock. So it will protect them all rather than having a lock for each independent lock for each resource. You can use a counting semaphore. Okay? So in this case, you initialize the semaphore to value n. Okay? N is the number of resources you want to protect. Okay. If n equals 1, this becomes the same as a binary semaphore. You're only protecting one resource. In this case, that's the critical section or a shared object. Okay. The value is n. You can basically use it to essentially protect n resources all at the same time. Okay. What that means is each resource can still be accessed by only one thread or a process at any given time, but no more than n processes can grab that semaphore at any given time. If you use it as a binary, you can only have one thread accessing the lock or the resource at any given time. If you have n, you can have up to n threads. And we'll see examples of how to use this. This is simply a definition of what semaphore is and what you can use them for. Okay? So I said the semaphore is an integer. Can you increment or decrement it using special atomic operations? Those operations are referred to typically as wait and signal. Wait essentially increments the value of a semaphore. Wait decrements the value of the semaphore, and signal increments the value of the semaphore. So there are two atomic operations that increment or decrement the semaphore, based on what value you initialized it to. Okay. So here is basically a use of a semaphore simply as a lock. Okay. We initialize semaphore S to value 1, okay. And then this is your critical section. You put a wait at the beginning, that's the same as acquiring the lock. You put a signal at the end, that's the same as releasing the lock. Okay. Now here is basically what wait and signal do. I said wait increments, decrements, and signal increments. So essentially the more formal definition is here. So wait will actually decrement the value, and if the value was non-zero before you decremented it, then signal will essentially not block that thread. It will let the thread in. Okay. On the other hand, if the value was 0, okay, when you try to call wait, then the thing will block. 0 essentially says the resource is in use. So when you call wait, it's basically saying the resource is in use, so you are going to block. Okay. Signal is going to do the opposite. Okay. If there is a thread that is blocked or sitting on the queue waiting for the semaphore, it will first unblock it. Okay. And if the queue is empty, it is going to actually increment the value. Saying that it's in. So you can see that if the value was 1, the first thread that goes in will decrement, okay, because the value was non-zero when you began. Okay, wait will not cause it to block, it will enter the critical section. Okay? Any subsequent thread that calls wait while the first thread is still in the critical section will try to decrement but find that the value has already reached 0, so it will be blocked at that point. It will not be let into the critical section until the first thread comes and calls signal, at which point it will be unblocked. Okay? Exactly the same semantics as using lock acquire and lock release. Questions here? Is this clear? Okay. All right. So just re-emphasizing what I already mentioned. Okay, that was too much milk using lock. So you had a lock acquire. That if there is no milk, go buy milk, release the lock. Each thread does the same thing. Okay, this is too much milk problem using semaphore. Okay, you say semaphore wait. Okay, that's and then if no milk, go buy milk and semaphore signal. Okay, so wait is taking the place of acquire, signal is taking the place of release. Okay, doing the exact same thing. Okay, so now let's try to think a little bit about how do you implement a semaphore. Okay, now we are talking about what is the OS to do, okay, in terms of implementing. Okay, so this is an implementation of the semaphore class. Okay, think of it as a OS level implementation or any library that implements a semaphore for some threads. Okay, so this is the class. There are two public methods, wait and signal. Okay, now I should mention that as far as OSs are concerned, they let independent processes also use semaphores to do synchronization. Okay? And you can also have threads library where threads do synchronization. Okay? So I have just given an implementation where processes are using a semaphore for synchronization. This could have just as well said thread T. If this is a threading library, then you are implementing semaphores for threads. Because OS level, you can also implement it for processes. Okay? Whether it's a process or a thread is not relevant to this discussion. Just keep that in mind why it says a process. Okay? So two public methods, wait and signal. Okay? There's a value of the semaphore. That's what you initialize it to. You initialize it to 1, this becomes a binary semaphore. You initialize it to some value n, it's a counting semaphore. Okay? And there's a queue, that's the wait queue. Okay? If the semaphore is basically gone down all the way to 0, any other process that calls wait will be actually put on the queue and blocked. Okay, that's our queue. Okay, that's a constructor. A value is set to whatever you want to set it to. And then the queue is empty. Okay, that's the wait implementation. That's the signal. Very simple implementation. Wait is simply going to decrement the value. Okay, and it will say the value is actually negative. Okay, it will say that the semaphore is in use, so it's going to put this thread or a process to sleep and put it on the wait queue. Yeah, if the semaphore is not available, you basically block the process. That's all it's saying. But if it was available, you just decrement and then you don't do this. You let the thread continue. It's grabbed the semaphore. Okay, and here is signal, which is doing the exact opposite. It is simply incrementing the value. Okay, value is value plus 1. If the value is less than or equal to 0, that says that the queue is non-empty. Okay, so you have to increment it and then pick the first process or the thread from the wait queue, unblock it, okay, so that it gets to enter the critical section. Okay. Yes, question in the back.
So not the value greater than or equal to 0, or was it less than or equal to 0?
Why is the value, okay, question is why is the value less than or equal to 0? So basically you could have just said, rather than looking at value, if queue is not empty, okay, take a process or thread from the queue and unblock it. So you will see that actually when the value turns negative, this is the point when you start putting threads on the queue, okay, because when the value is, initially let's say the value was 1, okay, first thread comes in, decrements, value becomes 0, okay, it continues, okay. Second thread comes in, value is actually getting decremented internally, it will become -1, and then because value is less than 0, that thread will be put on the queue. Okay. And the first thread that actually entered is going to call signal, you will increment the value again, so it will go from -1 to 0. Okay, so but there is the second thread is still blocked on the queue, so you will say is the value 0 less than or equal to 0, which it is, and you will remove the first thread. Okay. So if a value is less than or equal to 0, it essentially means that there is one or more threads on the queue waiting to be unblocked. If the value is greater than 0, that means that the queue is empty, the semaphore is available. Threads need not block. Okay, that's all we are checking. Yes.
So if we were dealing with semaphores that weren't binary, would we set it to like -1 for the value?
Okay. Question is, if you are using it as a counting semaphore, what would you initialize it to? You will initialize it to some value n which is greater than 1. So you say, let's say value is 3. Okay. So what that, if the value is 3, the first 3 threads that call wait will go in without waiting. The 4th thread will have to wait because at that point the value will go negative. Okay. Yes. Okay, that's a good question. So question is, when do you actually want to use this as a counting semaphore? So it is used to protect multiple resources, okay? Not just one. Okay? Typically, if you have a critical section, you never want to do this. You only want one thread to enter. You never have a case where I want 3 threads to enter this critical section because that simply defeats the purpose. So concrete example may be as follows. Let's say you have a bank of printers. Okay, you want to print a job, okay, but you actually don't. You typically, in this case, let's say you don't choose a printer, you just simply tell the print server print, and the print server simply picks the first idle printer and prints. Okay? So there can be, if there is a bank of n printers, there can be at most n processes printing simultaneously. The n plus first process will have to wait until a printer becomes available before it can print its job. Okay? So in that case, the print server will use a counting semaphore. It will set the value to n. Okay, first job comes in, it'll send it off to an idle printer, the first one. Second comes in, it'll send. So after, let's say there are 3 printers, all 3 printers are in use. If the 4th job comes in while they're still printing, that job will have to wait. Okay? In this case, we don't care about which printer is being used to print. Okay? If you cared about this job has to be printed on the first printer, then you would never use a counting semaphore. You will take each printer, which is a shared resource in this case, protected by its own semaphore. If you have equivalent, identical resources, you don't care which one you get. That's how you would do it. Okay? Another concrete example is, let's say you have a pool of threads, and let's say you have a web server. Okay? That's accepting HTTP connections. Let's say it's a web server, right? So it accepts HTTP connections, and each request comes in, it's assigned to a thread saying go service this HTTP request. There is a pool of n threads. You will protect them with a counting semaphore n. If more than n requests come in simultaneously from independent users on the internet, the n plus 1th request will have to wait because there is no idle thread. In this case, it doesn't matter which thread services the request. You just want one thread and say go service this request. Okay? These are all scenarios where you would use a counting semaphore. Any questions? Yes. All right. So one important point I didn't mention is that wait implementation and the signal implementation has to be atomic. Just as in a lock, we said it has to be atomic. So they will either be guarded by enabling and disabling interrupts, exactly what we showed for locks last time. We have ignored that. Okay? Or you have to use test and set. Okay? Because when these are being run, you don't want the scheduler to swap it out and bad things to happen. So this implementation is atomic, which means that you will either use a guard statement and a test and set instruction, or you will disable interrupts at the beginning of the method and re-enable them at the end. So the whole process runs without being interrupted once you start executing. Okay? So the same concepts that we talked about for locks last time will apply here. Okay, I just didn't show the additional steps that you need to put in there to sort of ensure atomicity. Okay? But exactly the same concepts will apply here. Okay? Any questions about this? All right, so quick example. Okay, before this is going back to the question of what happens when the value is not 1, initialized 1, but some higher level value, which is it's used as a counting semaphore. Okay. So here, let's say that there's a single semaphore, S, its value is initialized to 2. Okay, there are 2 jobs, P1 and P2, that are just calling wait and signal in some random order. Okay, there's 1 wait followed by 2 signals, and that has 1 wait followed by signal. So the question is, what happens to the value of the semaphore and what happens to the queue? Which one blocks, which one gets to continue? Okay. So you can just simply work through each of this wait and signals and just watch what happens to the value, and you can figure out what will the wait do for you. Okay. So first process calls wait. Okay. Value, so you just blindly execute this code. Okay. Whatever I showed there, which is you will decrement the value. If the value is negative, you will block. Okay. So first process calls wait. Okay. Value goes to 1. Okay. That's not a negative, so basically Q is going to be empty. Process P1 will continue, won't block. Okay. So P2 calls wait as well next. Okay. Value is going to go from 1 to 0, and decremented further. Okay. 0 is not yet negative number. Okay. So that process will also, P2 will also continue, okay, not block, so it will continue executing. Okay, so you have called wait twice. Value has gone from 2 to 0 at this point. Each time you decremented it by 1. Okay. Now you basically call the second wait in P1. Okay, there are 2 waits and 2 signals. So let's say that wait is executed next. Okay, so what happens to the value? -1. Okay, that's negative. Okay, so the value at this point, the third wait will become -1. Okay, 1, 0, -1. Okay. At that point it's negative, so P1 will be put on the queue. So queue is no longer empty. P1 is stuck on the queue and P1 is blocked. Okay. P2 is going to continue executing. It hasn't done anything, so it's continuing execution. And P2 calls signal next. Okay. Signal will increment the value. Okay. So it's going to go from -1 back to 0. Okay. And you also check the queue and you unblock P1. So queue becomes empty again. P1 becomes unblocked, so it starts executing. P2 is not blocked when you call signal, so it will continue executing. Okay. There are 2 more signals here. All they do is they continue to increment the value, so it will go back from 0 to 1 and 1 back to 2. Okay. So at the end of this, you took the value all the way from 2 to -1, brought it back to 0, and different things will happen depending on the value, whether you get blocked or not blocked. Okay, so from the semaphore classes perspective, some collection of threads or processes are simply calling wait and signal. All you're doing internally is checking what's the value after increment or decrement and what should I do. Would I block the thread that called it or let it continue? Okay, or unblock it in the case of signal. Okay, is that clear? Okay, so there is another exercise which I'm going to leave as a sort of a homework for you to go back and look. Same kind of stuff. Okay. What we will do is actually talk about a little more interesting stuff that you can do with Semaphore. Okay. What we have simply seen is how do you use it as a more glorified lock, okay, but not anything special. Okay. Now we'll see what more you can do. Okay. So we already saw how to use it for mutual exclusion. This is where you can set the value to 1 and then you always call a wait at the beginning, signal at the end. Okay. But there are more interesting things you can do, and one interesting thing you can do is with semaphores is express some scheduling constraints. Okay. You can express the order in which you want some code to actually execute independent of what the scheduler is doing. Okay. Typically, if you have threads, you don't have control over in what order the threads will execute. That's left to the CPU scheduling algorithm. Whatever the scheduling algorithm does, that's how the threads will execute. But suppose your application requires that some code has to execute before some other code for correctness reasons. Okay? You can use semaphores to enforce that constraint, enforce that ordering. Okay? That is referred to as scheduling constraint. Okay? And I'll give you some examples. Okay? In fact, we have plenty of examples in the following slides, but let me construct an abstract example. Okay, let's say there are 2 threads, A and B. Okay. And let's say we want thread B to wait for a certain operation foo to be done before it does something else. Okay, let's say thread B has to do operation bar and it wants foo to be executed before bar is executed. Okay, so what we will basically want to do is, let's say thread A is the one that's going to execute foo in this case, and we want B to wait until this execution is finished before it continues and executes something after foo. In this case, that's bar. How do you enforce this restriction using semaphores? Okay, that's really what we are going to look at. Okay, and what we want is, regardless of the order in which the CPU scheduler picks A or B, you always want this code in your program to be executed before that code is executed. Okay, rather than bar, let's just call it post foo. This is the post foo code. So how do we do this? Okay, so let's look at semaphores and try to figure out a way to do this. Okay. So whenever you want to express scheduling constraint, you will use a semaphore, but you will not initialize the value to 1 or n, but you will initialize the value to 0. Okay. So we'll say, let's say semaphore S, and we'll initialize the value equal to 0. Okay. And the way you enforce scheduling constraint is actually very straightforward. What you will do simply is do this. Okay. If you want some other code to execute before this code, then what you will do is you will essentially put a wait here. Okay. And this is the other code that you want executed first. You are going to put a signal there. Okay, by doing this, what you ensure is that this block is always executed before that block of code, independent of whatever the scheduler does. Okay, it doesn't matter whether the scheduler is going to pick A or B for execution. No matter what happens, okay, you are guaranteed that this code will execute before this code. Okay, let's ask why. Okay, yes, question. Okay, so you don't have to tell. The question is, do you have to let the CPU know? You don't actually control what the CPU scheduler does. Okay? You can't tell the CPU scheduler, go execute this program first. Okay? There is no way to tell it that. Okay? The only way we are going to force it to do that. And here is how. Okay? Let's just understand what happens. Okay? Let's first take the case, because we want this code to execute. Let's take the bad case where the CPU scheduler picks thread B for execution first. Okay, this is not what you want to happen, but let's say it picks it for execution. Okay, it's going to simply come and execute the first instruction, which is semaphore wait. Okay, so what is going to happen at this point?
The value goes to -1.
Okay, the value was initialized to 0, not 1. So if this code starts executing first, even though you want it to execute later, it's going to call wait, and the value is going to become -1. Okay? And because the value becomes -1, thread B will immediately block at wait. Okay, so this is blocked. If you start executing first, you automatically blocked it. Now the code cannot execute anymore. Okay? Then subsequently the CPU scheduler will come and start executing it at some later point in time. Okay? You will execute that function foo, which is some random arbitrary piece of code that you wanted executed first. It will now execute, okay? And then the code will call signal. Okay? So when you call signal, the value will go back from being -1 to 0, and you will explicitly unblock B. That's what signal does. The queue is not empty, it will cause it to unblock. At that point, B will subsequently become ready to run again. Okay? And when the CPU scheduler chooses it next, it will execute this code post foo that you wanted to be executed after foo. Okay, so now you are guaranteed in this particular execution that this will execute before the other. Okay. Now take the other scenario. Here, this scenario B was chosen first for execution, and we made it block because we didn't want it to execute first. We forced the CPU scheduler to block it by clicking a semaphore. Okay, so we'll take the other scenario. Okay, still initialized to 0, but now the CPU scheduler picks A for execution first. Okay, so you execute foo and you call signal, say. Okay, so as soon as you call signal, the value is going to go from 0 to 1. Signal increments. Okay, so value is 1. So A is done, let's say. Now B is chosen next. This is exactly the order in which you wanted things to execute, which is foo had to execute before this code post foo. So foo was already executed, value is gone to 1. Now you call B. Okay? You call wait. That's the first code, first instruction in the code. So what's going to happen now? Okay, you will decrement it to 0, signal decrements, okay? But 0 is not negative, so this is not going to cause this to actually block. You simply decrement and continue, okay? Because by decrementing and going to 0, you know that foo has already executed, which is why the value is 1. So you had initialized to 0. The only way it could have gone 1 is that other code has already executed and you called signal in that code. So there is no need to wait because foo is done. So you can simply not wait and execute. So even in this case, this code will execute before that code. Okay, yes.
In the first case, when the value gets turned into -1, it goes and does, if it executes A at a later time, it will get incremented to 0.
Yep.
And then it will go back to B.
Once you increment it to 0, if you look at the code for signal, right? So value was -1. Let's say this signal is called. You will simply execute this method, which will use value is value plus 1. So it goes from -1 back to 0. You will say is value less than or equal to 0. 0 is less than or equal to 0. Pick a sleeping thread from the queue, unblock it. So the sleeping thread is actually this thread. You will unblock it. So now it's ready to run. The CPU scheduler will at some point pick it from the ready queue and run it. It may not execute immediately afterwards, but at some later point in time. All we simply wanted was this code to execute before that code. It's not that they're going to execute one after another, but just in time, the first piece of code executes before the second piece. And that's exactly what we enforced. Is that clear? Okay, so this is an abstract example. I just said foo and post fee. We'll construct some real examples where we actually want some code to execute before some other code and see why. Is that any questions there? Here's a simple example of one such scenario. Let's say you want to implement the join or the wait PID method where you want a thread to wait for another thread to finish. Remember there was a wait system call. So one way to implement something like that would be you use a semaphore, initialize it to 0, and the first thread that's waiting for the second thread to finish simply going to do a wait and it will get blocked immediately. And when the second thread actually finishes, internally the OS may try to do a signal, okay, and unblock the first thread that was waiting for that thread to finish. Okay, somewhat contrived example, but that's one scenario. Okay, here's a better one. Okay. This one is taking us back to producers and consumers. Okay. Let me remind you what producers and consumers were again, if you forgot. Okay, producers, consumers, an abstract synchronization problem where there are threads called producer threads and threads called consumer threads. Producers are simply producing some data and sticking it into a shared buffer. Consumers are consuming data from the shared buffer. Okay, so there's some shared buffer which is an array, let's say. Okay, a producer thread simply produces data and consumer thread consumes it. There are many examples of producers and consumers. The print example I just gave you is an example where this could be a print queue. This is a job that prints. This is the print server that takes the print job and sends it off to a printer. Okay. So this basically any application can say print and stick a job into the print queue, which is a shared variable, shared buffer rather. And the consumer is in this case the print server. It will wait for a print job. As soon as one arrives in the queue, it will take it and it will send it off to printer. But there are many other examples like this. Okay, so producers and consumers. In this case, we do not limit the number of producers and number of consumers. You can have arbitrary numbers of these. Okay? So there could be many producers and there could be many consumers. Okay? They all share this single array. Okay, now let's ask the following question. The code is a little more complicated. Before I explain the code, let's talk about some concepts of what are the correctness properties for this application. What we want to achieve with producers and consumers. Okay, what are some simple things that you may want to enforce on this program? Yes.
The producer doesn't produce more than the queue can hold, and the consumer doesn't consume if it's empty.
Okay. That's something. Same thing. Okay. All right. So we could make this, so I didn't actually explicitly say this, but this queue could be bounded or it could be unbounded. This is a bounded queue. Think of this as an array of size n. Okay. That means the shared queue can hold a limited amount of data, up to n items. Okay. So that basically says that you can produce up to n items, and if this queue fills up, any other producer that wants to produce some data item has to be made to wait until some consumer is going to take some data item from this queue and make a slot available. Okay. If this is a bounded buffer, a producer can produce at most n data items before additional producers have to block, because there is no more space, the queue is filled up. So you will block producers. Okay. But there's an even simpler correctness rule than that, which is a consumer cannot consume anything until a producer has produced something. The queue is empty, there's nothing a producer can do. Okay, this seems obvious. Right? A producer cannot produce, a consumer cannot consume something before a producer produces it. That seems quite obvious and straightforward. But if you think about it, we just expressed a scheduling constraint. Okay? We said the consumer shouldn't run until a producer has run and produced something. There's nothing for a consumer to do if the producer has not done anything and the queue is empty. Okay? Simple scheduling constraint says that a producer must run before some consumer will actually run and do something useful. Okay? So now you will see where the scheduling constraints are coming in. Okay? So very simply put, let me just make sure that, just to simplify, let's assume we start with just one producer and one consumer. Okay? But this code works for n, doesn't matter. Okay? So to express this scheduling constraint, this is what you will need to do. Okay, so your code, this is the template code, it's not all complete. So you say produce data, stick it into the queue, and then you will say some semaphore signal. This is our scheduling constraint. This semaphore will initialize to 0, and then we will essentially say semaphore.wait, and then you write the code for consuming the data item. Okay? These two pieces of code have to be ordered, because there's nothing to consume if the producer hasn't run first. Okay? And we cannot tell the CPU scheduler that you must always pick this thread, schedule this thread before that thread. We cannot tell it that. The CPU scheduler will do what it wants to do. Okay? Yet our code must run correctly. We must ensure that the producer actually executes first, regardless of what the CPU scheduler does. And this is why we will need to use semaphores as a scheduling constraint. Okay, this is the first scheduling constraint in the program, which is you will let the producer produce a data item, and then you will make it signal that semaphore, and then this one will wait. So same thing I showed you last time. This is your foo, and that's post foo. Okay, this will guarantee if the consumer was chosen to be for execution first, it will immediately block if the queue was empty. Yeah, I didn't show you the queue was empty, but in this case, it will immediately block. Okay, that's scheduling constraint 1. Yeah, I'll say that this program has a second scheduling constraint. What might that be? The first one is we say that the consumer must run after the producer has run. Anyone have thoughts on the second one? Yes?
Yeah, don't produce more than you.
Okay. The second scheduling constraint is you cannot produce more than what the queue can hold. Okay, if the queue is full, there's a second scheduling constraint you have to enforce. If the queue is full, you cannot let threads run in whatever order they want. When the queue becomes full, a consumer has to run before the producer can run. Because when you have to force a consumer to run when the queue is full and empty up a slot before the next producer can run. If producers try to run when the queue is full, they have to be blocked. Okay? Is that clear? So the second scheduling constraint says that when the queue is full, that scheduling constraint comes into play only when the queue is actually full. Otherwise, it doesn't do anything. Okay. So what we will then do is we will essentially say that you will make the consumer run when the queue is full, and then you will basically have the producer run. Okay. So you will essentially do the same thing. You will use signal and semaphore, but you will do that at the beginning. In this case, what you are actually going to do is you will use a counting semaphore to enforce this scheduling constraint. So you use a second semaphore, let's say S prime is N. Do the following. So you will essentially, the producer will now do a wait on the second semaphore, which is basically going to check whether the queue is filled up or not. You will initialize that semaphore to N. Okay. What that means is the first N, if these are N threads, the first N threads can run without being blocked. Okay, because each of them will decrement this semaphore until it goes to 0. The N plus first thread also tries to run at the same time. This will basically become 0 and you will block. I mean, it will become negative and you will block that producer. And the consumer is actually doing a signal at the end saying, I consumed a data item, so now you will basically let a producer run. Okay, by signal, you are actually waking up any sleeping producers. Okay, so two scheduling constraints. First is when the queue is empty, a producer has to run before a consumer can do anything. Okay, so you enforce that as a scheduling constraint. When the queue is full, there's a different scheduling constraint, which is the consumer has to run first and empty up a slot before any other producer is let in. Okay. So you will actually represent this scheduling constraint by two different semaphores. You can't use the same semaphore to implement multiple scheduling constraints. Each semaphore implements a single constraint. The first one, which we call S, allowed the producer to run first when the queue was empty. The second one, which we call S prime, allows the consumer to run first when the queue is full and only when the queue is full. Otherwise, you don't care in what order they are. They can be concurrent in any arbitrary order. Okay. So now we have sketched out our solution. Okay. This is where we are using semaphores to force certain ordering of how things execute. Okay. This code is actually essentially doing that. It actually has 3 semaphores, not 2. Okay. The first 2 semaphores do essentially this. The third semaphore acts as a lock. Okay. The shared array is actually a shared data. Okay. So whenever you try to either put a data item in or take something out, you want to protect it as a lock. Okay. So your third semaphore is essentially going to be a binary semaphore. That's simply a lock. Okay. So you will see that there are 3 semaphores here, or there are 3 semaphores here. The Mutex semaphore is acting as a lock on your array. Okay. The empty semaphore is simply counting if it's going to simply count down and tell you if the queue has a single non-empty slot. That's this S prime. Okay. The full semaphore is doing the other thing, other scheduling constraint, which is a producer has to run before a consumer runs. Okay. So these are the 3 semaphores. The Mutex one you will initialize to 1. Okay. That's simply a lock. Okay. This is the first semaphore S, which you initialize to 0. This is the other semaphore N that we initialize. That's S prime. Okay, so this code is simply implementing what we've just done. The next question.
Why do you need 2 semaphores to keep track of the free slots and the used slots? Why couldn't you just keep track of one or the other and then compare with them?
Yes. So question is, why could you not use? Why do you need 2 semaphores to count the number of slots? Could you not have just done 1? Okay. The other thing you could have done here is to explicitly keep track of the number of empty slots and simply block based on that value. Okay. That's an alternate implementation. In this case, we are never explicitly tracking the number of free or empty slots. Okay. What we are simply doing is letting the semaphores count up or down and reasoning about is the queue empty or non-empty simply by looking at the value of the semaphore. Okay. That's implicitly telling us what that is. Okay. When we do monitors, we'll see that you could just use a single variable to track that. Okay. That's a simplification. Yes. Okay, so if you keep track of a single variable I that tells you how many empty slots there are, that's a shared variable. So you will have to protect that by a lock if you want to check its value. Anything shared, you have to protect by mutex. That's critical section. If you have multiple of them checking, one may be incrementing, others decrementing, bad things will happen.
So
Okay.
if you want to do it that way, you still have to change Semaphores. So you're not getting rid of them, right?
You can basically get rid of one. You can actually do this whole thing with just a single mutex if you could go to sleep, which we will see when we do monitors. Just hold on for a little bit. You'll see an implementation using monitors that's coming down. Okay. The point of this is we will basically go through it, we'll convince ourselves that it works, and then we'll say this is a little too complicated. Okay, then how do we simplify it, and we'll use monitors to simplify it. That's sort of the way we want to do. But let's first convince ourselves that this works. So basically if you look at, the comments are overflowing, it doesn't look clean. So you'll see that adding and removing data items are protected by a lock. That's a mutex. So you do a wait and signal. So this code is simply adding or removing data items from your queue. Okay, this code. Okay. And so that you always do an acquire and release, which is wait and signal. That's all you do. Okay. The first line there is basically, or the last line here is doing the signal, which says the producer runs first, and then this one is going to do a wait. If the consumer thread starts running and no producer has run, you'll immediately block because full has been initialized to 0. Okay. By initializing semaphore full to 0, if the consumer runs first, if the value decrements to negative and becomes negative, and consumer will immediately block. This enforces the constraint, scheduling constraint, that the producer has to run first. Okay. And the producer is also going to do the same thing there. It's going to do a wait on empty, which was initialized to n. Okay. So the first n producers can go and start producing data item. The n plus first producer runs before any consumer has run. Okay, the value will go to negative. Okay, because it will get decremented n plus 1 times, so it will go from n to minus 1. So the n plus first producer will block. Okay, that's enforcing the constraint that the queue is now full. No consumer has run yet. No additional producers can run before a consumer runs. That's our scheduling constraint when the queue is full. Okay. So those are two different semaphores that are trying to enforce two different scheduling constraints. The wait and the full. The empty and the full. Okay. This is exactly this code that I just wrote here as a template that's being produced in a little more detail there. Okay, is the concept clear? I mean, the basic point that we are doing with semaphores is enforcing some scheduling constraints, which is you want to enforce order in which code runs. And this should be independent of what the CPU scheduler does. We have made no assumptions about how the scheduler will pick thread. Is it round robin? Is it doing shortest job first, or whatever the scheduling policy? This code will always execute correctly. We are not depending on the scheduler to do the right thing. The scheduler can do arbitrary things and the code will still do exactly what we want it to do. Yeah, because when you have concurrency, typically you don't control how concurrent threads execute. But if you want so this is synchronization where we're enforcing constraints on how we want things to execute. And that is required for correctness of the code. Okay? So this is just showing pictorially what's happening to empty and full, which I will just ignore. I've already explained that example. So this is quick summary of semaphores, and we'll spend the rest of the time on monitors. Okay, semaphores are a generalization of locks. Okay, we use them for 3 different purposes. You can use it as a binary semaphore, which is same as a lock. You can use it as a counting semaphore, where it's the equivalent of locking up to n resources. A generalization. And the third one is you basically can use it to enforce scheduling constraints. One thread can be made to wait before some other thread has executed some code. Okay. And simply the way you do this is by initializing the values differently. Okay. Counting semaphore, binary semaphore, initialize it to 1. Counting semaphore, initialize it to n. Scheduling constraint, initialize it to 0. Just by picking different initial values, we are using the same primitive in 3 different ways. Yes?
So when you pick the initial value, then you know that's the max that's the max resources. If I do a binary one, it starts to 0,
If you initialize it to 0, it's typically used to enforce a scheduling constraint. But you can, of course, increment the value as many, if you call signal multiple times, it will keep incrementing. Okay, it's not going to restrict the value to just 0 and negative. You can call signal and keep incrementing.
So the same object would be the same Semaphore to be binary or object.
Yes, of course. So just because you implemented it doesn't require the code to use it as a binary. That's the typical way you use it. Okay, that's another problem is you have to sort of, it's an overloaded construct. It's being used in 3 different ways just by picking a different initialization. Okay, so now let's move on to the next construct, which is monitor. Okay. And as part of that, we'll also study condition variable. So we'll first try to have a discussion of what's wrong with Semaphore. Okay, so we already know what we just said is something that's some good has come out of it, but there's some confusion that may result, okay, because Semaphores have multiple issues. First is you can use the same construct to do different things. And you really have to look at the code, you really have to look at the initialized value to understand how the semaphore is actually being used. Okay. Locks are very simple. You can use them for one and only one purpose. So if you have a lock in the code, you can be pretty much guaranteed it's just simply guarding a critical section. Now if I give you some code with a semaphore and say, what is this semaphore doing? You actually have to read the code, understand what the code, how the code has been written, reason about it, and then say, oh, this is a counting semaphore, or this is enforcing a scheduling constraint. Okay, but just by saying it's a semaphore, you don't know what it's being used for. That is confusion. Okay, it's overloaded construct. So you don't want that. You want sort of clean code. Because especially if your code doesn't work for some reason, you're trying to debug it, then you will not understand what is happening because you don't understand exactly what the semaphore is being used for sometimes. And if you make a mistake in initialization or you put the weight and the signal in some wrong places, then you will have some deadlocks or some bad things. Okay? So that's one problem. Okay? So the other problem is there is no direct connection between a semaphore and the code it's trying to protect or the data it's trying to protect. Those are two, they are declared independently, they are used together in the code. Okay? So you will have to actually look at the code and try to find the connection. What is the semaphore connected to which critical section and so on. Okay? And there is no guarantee of proper usage. It very much depends on the application programmer writing correct code. It's very easy to make mistakes with semaphore. Locks, it's hard to make mistakes. I mean, you can make a mistake. You can forget to write release when you acquire a lock, and your code, the thread will just stick with the lock it acquired, never release it. But that's easy to find. Okay, here the weight is in one thread, the signal is in some other thread. You have to actually look at code in different places in your program and reason. It's much harder to debug. Okay. So what we want is to do all of this stuff, but with higher level of abstraction. So it's much easier to understand what the code is doing. We still want to have critical sections. We still want to enforce order of execution and whatnot, but not with all this complication. Okay, so we'll achieve that with monitors. Question?
Is there any reason to use the semaphore as a lock instead of an actual lock?
Yeah, the question is there a way to use a semaphore as a lock instead of an actual lock? The answer is yes, and this is the way to do it.
Is there any reason to do that? They both do the same thing.
Oh, is there any reason to do that? There is no reason to do it other than if your programming language, let's say, only supported semaphores. With some programming languages too, because it does everything a lock will do for you and more. And some will support both. If they support both, you just use locks. Okay, if they only support semaphores, then this is the way you use it. Okay, so basically what we are saying is we like some of the features that semaphores have given us, but not the part that they made our code messier. They require us to think, okay, so I want this to run before that, so I better put a signal here, a weight there, I better initialize it properly, etc., etc. Okay, that is a little more complicated code to think about. Okay? And this is a relatively simple synchronization problem. Okay? In reality, when you have complicated application, there are a lot more complex scheduling constraints. Okay? That makes things even messier to implement using Semaphore. So you want a simpler construct and you want something at a higher level, and that's monitors. Okay, so we'll start with the definition. Okay, we'll see usage and then we'll think about implementation. Okay, that's the usual way. So what is a monitor? Okay, think of a monitor as very similar to a class, whether it's a C++ class or a Java class, it doesn't matter. Okay. It's a class that has data and methods. But it has, in addition to that, it also allows synchronization to tie all of the code and the data together. Okay. It's a special class that has methods, it has data like any other class, but it also supports synchronization out of the box. What does out of the box mean? It basically means you don't have to declare locks, you don't have to acquire locks, you don't have to release locks. The system will do it for you. Okay, typically, so far, whenever we have looked at lock semaphore, you, the application programmer, actually has to declare that there is a lock. You have to put an acquire and release in the right places. In this higher level construct, we will not ask the programmer to do any of that. The system will internally do it for you. It will acquire locks and release locks automatically for you. Okay, how that is going to happen, we'll talk in just a moment. Okay, so in other words, synchronization is built into the implementation of the class. Okay, so the monitor will guarantee us mutual exclusion, which means that if there are multiple methods that this class exports and there's an object you declared, only one thread can call any method of this class. If two threads try to invoke methods of the class at the same time, the second thread will be automatically blocked. The monitor will guarantee that for you. Okay. So code of this class is automatically going to enforce mutual exclusion, which means any thread can call at a method, and if any other thread tries to invoke either that same method or some other method, that thread will be blocked. We will also make all the data private, which will require us to actually call a method in order to access the data and also enforce mutual exclusion. Okay, so here's a slightly more formal definition, which is a monitor will declare a lock and some things called condition variables. You, the programmer, don't have to do much. Monitor will automatically have a lock whenever a thread enters, or have a thread grab a lock when a thread calls a method. Okay? So think of this as the class where internally the system has generated a lock acquire and a lock release as the first instruction and the last instruction of every method you write automatically for you. So whenever you call a method, you have to first acquire a lock on that object. The system will do it for you. You don't actually write the code or even see that code. Okay. So basically this is how it is going to work. I'll talk about condition variables in a moment. Okay, and let me show you some code. Maybe that will make it simple. Okay. So since you all know Java, it's easy to understand monitors in Java. Okay. Java has built-in support for monitors. Okay. You can take any class you have ever written in Java and turn that into a monitor. Okay. Simply by using one word, which is synchronized. Okay. You take any Java class, any methods you have written for that Java class, to add the word synchronized in front of that method, okay, automatically what that tells JVM is now this has become a monitor. Internally there you have to declare a lock, and whenever any thread calls that method, okay, it has to first grab an internal lock. Only one thread can execute that method at any given time. This is now automatically guaranteed. Okay. So simply by adding the keyword synchronized in front of any Java method of a class, okay, you turn that class into a monitor. Okay. The only things you have to guard is any data, any variables has to be made private, so it cannot be accessed and modified from the outside. They can only be accessed by the methods of this class alone. Okay, yes, question.
If you have a monitor that's if you have a function synchronized and that calls a function that touches data that's not private, does that work?
So typically what you want to do is, if the synchronized method calls another method, okay, and that accesses some data, if the data is internal, it's private, so it's automatically synchronized. If the data is external, okay, then some other thread that is calling that can access it might modify it also. So in that case, you will not get mutual exclusion.
So if the second function you're calling within the synchronized function, it doesn't matter if it's synchronized and the data could be called and everything, then that would work, right?
No, it would not work. I just said it would not. So if within a monitor you access external data, that let's say belongs to some other class or is some global variable, that is not guaranteed to be synchronized, or that's not guaranteed to be mutually exclusive, because some other thread can directly access and modify it without coming through this method. So if you are allowing something else to access that data without a lock, then you are not going to get synchronization. Okay? So if you want to protect a data item, you want to put it as a private inside a monitor and only access it through the methods. That's the only way you'll guarantee. If you start mucking around with external variables or global variables, some other threads could muck around with them also without going through this class. So then it's not protected at that point. Okay. So coming back to this, so it's very straightforward to implement or use monitors in Java, supported out of the box. Just use one keyword and then you turn the class into monitor. Here's an implementation of a queue. Okay. So it's class queue. So you have, let's say, an array that holds item on the queue. So you have two methods, add and remove. Okay. Both you will see are synchronized. All that the add method does is put an item on the queue. Okay. And when you call synchronize, it's guaranteed that there is a lock that you have acquired. So when you are putting an item on the queue, this queue is a shared data structure. This thread and this thread alone can access that queue, no one else. That's guaranteed for you because you have to grab a lock in order to enter. Okay. The same lock has to be acquired in order to remove a data item because you made this synchronized. And here you are simply saying if the queue is not empty, remove a data item. Again, modification of the queue is protected by the lock. Okay. So very simply, without using any additional constructs, you have turned this code into a monitor, you have enforced mutual exclusion and whatnot. Okay. So now you can look at the code and see whether you like this code. Is there anything you can see that we can improve? Okay, there's nothing you can improve and add. All you're doing is adding an item to the queue. Okay. But in remove, we say if the queue is not empty, remove an item. Okay, that's the right thing to do. Okay, but we didn't say anything about what to do for remove if the queue is empty. So suppose you call remove. Okay, and you always want remove to successfully return a data item from the queue. Okay, what would you do? Yes?
You have to make sure that adds all the thirds.
Okay. So if you want the remove to always successfully give you an item from the queue, the only way to enforce that is if the queue is empty, somehow you want the add to run first and put something onto the queue. Only then can remove successfully take something out. Otherwise the queue is going to be empty. There's nothing to remove from the queue. Okay. So if you want to enforce that, that's a scheduling constraint. Okay. So if you want to enforce that, the only way you are going to enforce that is to say if the queue is empty, go to sleep. Okay. Wake up this thread when something else will actually, some other thread is going to call add and add a data item to the queue. That's the only way you will ever say, when I don't care when I call remove, but always remove should return a data item. Only way it will happen is if the queue is not empty, you get that item immediately. And if it is empty, you block until add is run first. That's a scheduling constraint. The way you are going to enforce that scheduling constraint is you want to do something in the code here that will say if the queue is empty, go to sleep. Let somebody come and add a data item and then wake me up. Okay. Somebody has to then wake me up as well. Otherwise, I'll sleep forever. Okay. We will enforce this using this construct called a condition variable. Okay. So what we want is we want to change remove to wait until something is on the queue. Okay. So now we want to logically go to sleep inside the critical section. Remember that this code is a critical section. Okay. If you simply actually put a sleep here, a real sleep, okay, this code is just not going to work. Okay. Simply because you are holding the lock and you went to sleep. Now somebody else calls add, you won't get the lock because you are holding it and you've gone off to sleep. Okay, so there is some subtlety here. So if you go to sleep, you better make sure this lock is actually released. Okay. Now again, you don't want to write code to do all that. You want the system to do it for you. So you just want something elegant that will do automatically all of these things. Okay. So you want some functionality rather that will put this first remove thread to sleep inside a critical section, yet you don't want to hold on to the lock, because if you hold on to the lock, then nothing else will actually get to enter any method of this class. It's a monitor. Okay? So the way we'll do it is we'll use condition variable. So what a condition variable does is it checks a condition. That's the reason it's called a condition variable. And if that condition is true, okay, then you will basically go to sleep and atomically release the lock. And it's also guaranteed that when you're woken up, the condition may have changed from true to false, or maybe not, we will see, but you reacquired the lock. Okay, so when you go to sleep, you give the lock back, but when you're woken up, it's guaranteed that you have the lock back because you're still in a critical section. So you wake up and start executing some code in the critical section, the lock better be back with you. So you can yield the lock, but when you're woken up, the system will guarantee that the lock is given back to you. Okay? And so this is what a condition variable will do automatically for you. This is just how it works. Okay? The way you use it is as follows. It has actually 2 or in some cases 3 different methods. Okay? If you say condition variable dot wait, okay, the wait method simply puts that thread to sleep, okay, and it releases the lock that the monitor has actually given to this thread atomically. Okay. Some other thread can call wait condition variable dot signal, and if there is a sleeping thread, that thread will be woken up and given the lock back when it's woken up. Okay. You can also call condition variable dot broadcast, which can actually wake up more than one. Any thread that is sleeping for this condition to be true can all be woken up at the same time. We won't see the use of this as much. We'll see how to use these 2 things. Okay, so here is your code for the Q class. Okay, now same Java code. Okay, nothing has actually changed. So here what you will do is you will make this synchronized, put a data item on the queue, and you will call notify. Okay, so notify. So in Java you don't actually use the term signal. It's called notify, okay, which is the same thing. Okay, so wait is still called wait. Signal is called notify. Okay. So wait, so here we basically say while queue is empty, wait. Okay. This is called, you are doing a wait on a condition variable that's declared for you. So this will automatically give up the lock and go to sleep. Okay. So you are inside a critical section. So atomically you go to sleep and you give up the lock. Question?
Why are you using a while loop over a wait? Wouldn't it make more sense to use an if and then you break out of it? And then as soon as you come back, then you're already into the remove.
Yes, okay, good question. So the question is why, so I will come to that in just a second. Okay, so let me repeat the question, we'll answer it in just a second. Okay, here what we are simply doing is we are sitting in a while loop and saying if, or while the queue is empty, not if. The queue is empty, go to sleep, give up the lock. Okay? And when you are woken up, you will check one more time. If the queue is not empty here, you will go and remove that data item and everything is fine. When you are woken up, you have the lock back. The queue is still not empty, you will just go and remove the data item. Okay. So first, before we understand why you have a while there, let's ignore that for a moment. What you will see now is remove will always give you a data item. If the queue is empty, it will wait until the data item is produced. And if the queue is not empty, it will just remove it from the queue and return it to you. Okay. Add will simply add to the data item. This is actual Java code that will work. Okay. I mean, it's pseudocode, but if you just fill out all the missing detail, this is going to work. All you have done really is just add the synchronize. You don't see any locks. You don't see an acquiring of a lock, releasing of a lock. Internally, all that is actually happening. Okay, the JVM will put a lock acquire and lock release internally for you. You don't write any of that code. It's done for you out of the box. By just using this keyword, some system will do all of that. Okay, so you are doing less work in terms of writing code, synchronization code like this. Okay. Now you also have the ability to enforce scheduling constraints. Same thing we did in Semaphores. We said that you want that code to run first if the queue is empty. Okay, this is why we put a signal. Okay. If this was a bounded queue, which so far we assume the queue is unbounded. If there's a bounded queue, you could use a second condition variables which would have caused add to say if the queue is full, wait. Okay, do condition variable dot wait, some other condition variable dot wait, and then remove could have signaled it. Okay, so you can do the same thing you did for the Semaphore class. Here we are just implementing an unbounded queue, so only the the consumer or the remove method waits when the queue is empty. The producer just can keep adding and the queue will sort of grow unbounded inside. If you want to make it bounded, you would have a second condition variable that will cause the add to actually block until the queue has become non-full. It has at least one empty slot. Okay, much simpler code to write. Okay, now we'll come to this question: why is this a while and not an if? What would happen if you just simply change this code to say if queue is empty, wait. Yes, consumer runs first, says queue is empty, you wait, go to sleep, release the lock. Okay. Some other thread calls add eventually, okay. Puts a data item on the queue, calls notify and wakes up the thread. Okay. Notify will wake up the condition variable, any thread that's sleeping on a condition variable, it will wake it up and hand it the lock and it will wake up. So then why would it not be okay when you are woken up here to simply continue from the if and take a data item that was put in the queue? Yes.
Maybe if it got woken up by the wrong thread, and the queue wasn't actually, the queue was still empty, and you're not checking the queue again.
Okay. So you are saying maybe something could happen where you got woken up, but after you are actually executing, the queue is not empty. Then you would need to check. Yes, you have something.
Or if while it was waiting, another consumer was looking first, grabbed whatever was there, and now nothing is,
Yes.
now it's empty again and it gets woken.
Okay. So while you're woken up, but you're not running, some other consumer ran in the meantime and just grabbed that data item. So you are woken up, but then when you are actually executing, the queue has become empty again. Something else. So because this is concurrent code and we do not control what the CPU scheduler does, we still want the code to work. Okay? The example that was just given might well happen. First thread calls remove, queue is empty, you go to sleep. Second thread calls add, you put a data item into the queue and you call notify and wake the first thread up. Okay? At this point, the thread is just woken up and put in the ready queue of the CPU scheduler. It's not running yet. Okay? But before it could run, a third thread could come along and call remove. Okay? At this point, the queue is not empty because the second thread has just produced a data item. It will go and simply grab it. It will check, is the queue empty? No. Go remove that data item. Queue has become empty again. So in the meantime, after the thread that was woken up will again run. But now the queue has become empty. And we don't control what the CPU scheduler does. We cannot tell the CPU scheduler, this thread was sleeping, you woke it up, so better run this before you run some other consumer. You can't tell the CPU scheduler that. The CPU scheduler will do whatever it wants to do. Your code cannot depend on a CPU scheduler. The code has to work no matter what. Okay? This is why you do a while. I got woken up. Okay? Presumably some producer ran and produced a data item. So I will still check. I'm going to do a paradigm check. Did something else run and make the queue empty again? So this is why this is a while. Okay, right, answer your question. So when you use condition variables, you should put a while there. Okay, do one more check, and if the condition is still valid, nothing else has run and toggled the condition again, you will simply go and consume. Otherwise, you will go back to sleep. Okay, so some subtleties you have to keep in mind. Okay, okay, so we'll actually, yes, question.
So when the add calls notify, it still has the lock on the
Yes.
locker. So does the remove get called after add returns, or like does add release the lock when it calls it?
Okay. So a good point. So there's in fact both of these questions, the if question and this question will answer also in the second slide, next slide. So the question here is what happens when notify is called. So when notify is called, simply the one thread that is sleeping on the condition variable is woken up. Okay? At this point, you have not exited this method, so you are still holding. This thread is still holding the lock. This thread has been woken up, still doesn't have the lock. Now, after you exit from here, then you can get the lock. Okay? That's the general assumption. Okay? You could have actually called notify all, okay? Which means if there are 10 threads sleeping, they will all be woken up, but clearly not all of them can get the lock. When you call notify all, the next thread to run will actually get it, not all of them. But you can wake them up if you want. That's what notify all does. Okay. Now we'll come to both of these points and look at some other ways to implement semaphores, not semaphores, rather monitors. Okay. So there are two types of monitors. Okay, there's something called a Mesa style monitor and something called Hore style monitor. Okay, Mesa style monitor is what I just showed you. Okay. What it assumes is typically when you call a notify, okay, you still hold the lock. This is the question that was just asked. Okay, you hold the lock and the waiting thread has to actually grab the lock when it's woken up. On the other hand, there is another class of monitors now which you only find in textbooks. There are no implementations of it anymore, because most implementations simply do what you do in Java and what I just showed you. In this case, what happens is when you call notify, right, the thread that calls notify or signal immediately gives up the lock and transfers control to the waiting thread. Okay, so the waiting thread is immediately woken up and it's guaranteed to have the lock. So the control of the lock passes from the thread that calls signal or notify to the thread that was sleeping on the condition variable. Okay, this is how that monitor is implemented. Okay, as I said, this semantics are only now found in textbooks because there are no real implementations. Okay, so what do we get by this alternate semantics? Does it simplify anything? Okay, so I'll just run out of time, so I'm going to just show you one code here, piece of code, and then we'll end for the day. So if you had Hore style monitors, the only thing that changes is this while will become an if. Everything else is the same. Okay. The reason the while becomes an if is in Hore style monitors, when you call notify, okay, the semantics of the monitor is when you call notify, the transfer, the control of the lock goes from the thread that called notify to the thread that called wait. Okay? The lock is directly handed from this thread to this thread. No other thread. So if the thread log goes from this thread to this thread, you do not actually need to do while, because you're guaranteed that somebody woke me up and handed me the lock immediately. Nothing else would have run in the meantime. And even if it ran, it would have to block because it did not get the thread. Okay? So the only thing that happens if you have Hore style is the while becomes an if. Yes, because you don't have to check one more time. You're explicitly given the lock, nothing else ran in between. Okay? But in any real code, you don't do that. That would actually lead to incorrectness. Okay, or wrong code, you put a while like you have there. Okay, because most code actually uses Mesa style. Alright, so we'll end here for today and continue some of the remaining slides next time.